satellites and things like so. So we decided to give a small recognition of his work in the science divulgation. And unfortunately, he passed away. And that's the message I would like to present to you. The time do not wait for us. So every time we have an opportunity to have a contact with a professor, a colleague, international professionals, take that opportunity, because maybe you want to have another chance. Okay, so have a good time. We will start Charles or Jim. Oh, okay, so Jim, thank you.
Obrigado. Eu vou falar em português, se tá bom, pode ser assim. E, bem, vai acontecer que eu não sei umas palavras técnicas em português, então aí vocês vão me ajudar quando eu chegar a esse ponto. Então, eu vou falar com vocês brevemente sobre o clima espacial. Então, eu vou falar sobre o problema que existe, e o Charles vai dar a solução do problema, certo? I told him, I said, I'm going to talk about the problems and you're going to talk about the solutions. Tá certo. Então, o clima espacial, só para dar um contexto, isso aqui é uma imagem do telescópio que foi recentemente lançado, um ano atrás, James Webb Telescope, né? Então, essa imagem mostra um bocado, eu só vou botar um negócio em contexto aqui. Então, tem várias estrelas, mas a maioria que você está vendo lá não são estrelas, mas são galáxias. Cada galáxia tem uma diferença, cada um é como nós, cada um somos individuais, né? Galáxias também são individuais, mas são compostos de milhares de estrelas. Não diferente de como a nossa estrela chamada Sol. Se quiser baixar a luz, não, pode baixar aqui, eu sempre trabalho no escuro mesmo, não tem problema não. Certo. Então, então, tem várias galáxias. Essa daqui é uma simulação da nossa galáxia, chamado Milky Way. Em português é chamado Via Láctea, é certo. Então, dentro desse Galaxy existe um sistema solar chamado o nosso sistema solar. Então, isso daqui é só para dar um contexto que todo mundo sabe aqui, mas nosso planeta é bem pequenininho, uma estrela comum, mas vamos ver que essa estrela, mesmo comum, é importante para nós estudarmos. Por quê? Porque o nosso planeta existe dentro da atmosfera estendida dessa estrela. Então, entender como essa estrela funciona e qual o impacto que ela tem na nossa vida pessoal é importante. Então, isso é a coisa de clima espacial. Então, como é que é isso? Interessante. Então, essa daqui é vamos dizer, essa daqui é uma imagem artística, claro, do nosso Sol e também da Terra. Esse daqui é o domínio da heliofísica. Agora, heliofísica é como astrofísica, é uma disciplina de ciência que estuda a interação entre o Sol, nosso planeta, outros planetas do nosso sistema solar, e também a interação com o nosso Sol e o espaço interestelar, certo? Então, sempre estudando a física espacial sobre do volume entre os planetas e também incluindo o Sol. Então, quando você for para fora, você não deve fazer isso, mas se você olhar para cima para ver o Sol, você tem que ter óculos especiais, né? Então, não olhe para o Sol, mas se você tiver esses óculos especiais, você olha o Sol e só vê uma bolinha lá de gás. Mas a gente pode ver se a gente observa o Sol em outras wavelengths. Como é que se chama wavelength? Frequência. A gente vê que o Sol tem essas explosões, né? Isso daqui é a coisa que a gente tem de tomar conta, que a gente tem de entender. Por quê? Porque nós vivemos, né, na atmosfera estendida e, às vezes, essas explosões nos impactam. Agora, geralmente, a gente não pensa no que pode fazer, porque o impacto, geralmente, ocorre na região em cima da nossa atmosfera. Quer dizer, nossa atmosfera nos protege, também o campo magnético que a Terra tem nos protege. Mas, como a gente já está usando o espaço mais para comercial, para comunicação, para diversas coisas, os componentes, as aeronaves, as coisas que a gente está botando no espaço são afetadas. E também, daqui a pouco eu vou falar também coisas na Terra que são afetadas por causa da nossa tecnologia, certo? Geralmente, a atmosfera nos protege da radiação e coisas assim, mas tem coisas técnicas que a gente tem, inclusive, que a gente usa todo dia, que se tiver uma explosão, se tiver uma tempestade solar, pode nos afetar. Então, esta aqui é uma simulação que mostra que o Sol, às vezes, tem essas explosões, você pode ver nessa área vermelha, e quando solta um bocado de energia. Essa energia geralmente vem em três maneiras. Primeira maneira que chega à nossa Terra, se for diretado, diretado é a palavra correta, se for, como é? Direcionado, pronto, se for para nós, a primeira coisa que chega é a luz. Então, são os raios-x e coisas assim que são perigosos, mas a atmosfera geralmente absorve essas coisas, não tem problema. Para nós aqui na Terra, agora em cima é outra coisa. E a segunda é a radiação. Isso são partículas, principalmente prótons e elétrons, que vêm numa velocidade, não na velocidade da luz, mas metade ou talvez um décimo, e chega, em vez de 8 minutos, que é o tempo que leva para a luz chegar do Sol para cá, leva mais ou menos umas horas, dependendo da velocidade, certo? E da energia. Então, chega a radiação, é a segunda coisa. A terceira coisa é uma plasma que é chamado coronal mass ejection. Agora, não sei em português como é que se chama isso, mas é uma injeção da corona. Massa corona. Pronto. Pronto, isso. Obrigado. Isso aqui vai ser meu tradutor quando eu chegar nessa hora. Pronto. O que ele disse, se isso acontecer, então essa é uma bolha de plasma bem grande, e se for outra palavra, directed toward us, como é aquela outra? Se for direcionado para nós e chegar, vai fazer uma interação com o campo magnético, vai botar um bocado de energia no nosso campo magnético, e isso faz com que bota muita energia dentro da nossa magnosfera, que é a área que é dominada pelo campo magnético da nossa Terra. Então, e também já sabe, claro que todo mundo sabe que tem a Lua, né? Mas e também vocês estão sabendo que a gente vai voltar para a Lua agora, chamado Artemis, né? E a AEB está dentro desse projeto, então talvez a gente pode falar isso mais tarde, depois, mas isso é uma coisa muito grande, porque nós não só vamos para a Lua, mas vamos usar esse passo para ir para Marte. Então, a gente está olhando lá agora para ver o que é que nós temos que fazer para botar uma pessoa, não somente na Lua, mas também depois em Marte. Certo? Então, eu sou um cara velho, eu não vou botar ninguém em Marte, mas vocês são as pessoas que vão fazer isso, certo? É por isso que você tem que ser bem preparado para estudar. E como o diretor Moura disse, o tempo não vai esperar para ninguém. Então, é a hora agora para nos prepararmos para isso. Então, estamos fazendo essas coisas para ir para a Lua. Então, como é que a gente está fazendo? Essas daqui são muitas missões só na divisão da Heliofísica da NASA. Eu trabalho na sede principal, o headquarters da NASA, lá em Washington, D.C., e nós lançamos um bocado de missões para estudar várias coisas. E cada missão aqui tem uma história, tem um bocado de gente trabalhando em cada missão, tem um propósito, um objetivo muito importante para entender esse sistema de sistemas entre o Sol, a Terra, os planetas e a região interestelar. Então, você pode ver que a gente tem várias missões olhando para o Sol, tem várias missões aqui olhando para o vento solar, quer dizer, o plasma que está saindo do Sol, a gente chama de vento solar, e isso é que dá essas tempestades. A gente estuda muito sobre o campo magnético e como o campo magnético é afetado pelo vento solar. E também dentro da ionosfera, essa câmara bem em cima da nossa atmosfera, a ionosfera, a mesosfera, a termosfera, estudando essa área onde temos a transição do espaço, que geralmente é um vácuo, mas não é totalmente um vácuo, mas na nossa atmosfera. Mas não somente estudando o Sol e a Terra, a gente, olha aqui, estamos indo para Marte novo. Já temos o Themis Artemis, que são duas pequenas satélites orbitando, e voltamos daqui a pouco com um Gateway, que é sempre uma estação espacial orbitando a Lua, e depois o Artemis, que vai levar as pessoas, vai levar uma mulher, uma pessoa que não é, bem, que não parece comigo, não é branco, certo? Vamos levar, não sei como dizer em português, mas eu sei que não é político corretamente, mas eu disse mesmo. Vamos botar gente que parece com a gente, não comigo, mas com a gente lá na Lua, certo? Então, isso é importante, porque para estudar um negócio de espaço não é fácil, vocês já sabem disso, vocês estão estudando essas coisas, não é fácil. Precisa de todo mundo, cada pessoa traz sua experiência para uma solução de problemas. E diversidade é uma coisa muito importante para a NASA, por quê? Porque a solução de coisas complexas são feitas melhores com um grupo diverso, certo? Isso inclui quem é que vai para a Lua, vai ser um grupo diverso, aparece com a gente, com o pessoal. Então, isso é um tema, eu acho que eu vi esse tema também hoje de manhã, não foi não? Certo? Então, isso é um tema que, para fazer essas coisas difíceis, precisa disso. Bem, vou voltar para a minha história aqui. Também já estamos na Marte, já tem o Curiosity, que é o carrinho lá no Marte, e temos um instrumento lá, observando a radiação. Tem outra missão chamada Escapade, que vai para Marte, mas eu também vou mostrar uma outra coisa aqui. Aqui tem os CubeSats. CubeSats, todo mundo aqui já sabe que é um negócio bem pequenininho, desse tamanho, né? Uma caixa de sapato, coisa assim, desse tamanho, bem pequenininho. Tem muitos, e essas missões pequenas têm uma grande parte para estudar esse sistema todo, porque às vezes é melhor ter um bocado de observações feitas por muitos aeronaves pequenas do que um grande que faz uma medida, uma observação bem focado. Às vezes é melhor ter um bocado de observações, talvez feitas não tão bem, mas ter um bocado a gente pode estudar outras coisas. Então, temos esses CubeSats. Isso daqui é somente uma razão para ter muitos CubeSats. Então, a gente não está mostrando os CubeSats aqui, mas tem um bocado que estão e nós estamos trabalhando. Então, eu falei um pouquinho sobre o Sol, às vezes as coisas que saem do Sol. Essa daqui é a magnosfera. do planeta. Aqui essas linhas demonstram o campo magnético. Então essa interação, o impacto do Sol através do vento solar, aqui o solar wind, é muito importante para entender porque isso afeta as coisas que estão em órbita. Então essa daqui é uma simulação mostrando o vento solar que vem daquele lado para cá, e quando bate no nosso campo magnético, faz com que a parte aqui no lado que não está iluminado pelo Sol é estendido e às vezes reconecta, chamado reconnection, magnetic reconnection, reconexão magnética, eu acho que em português. E quando isso faz, a energia, principalmente dos eletrônios e prótons, estão carregados de volta para a Terra, e quando essas partículas entram na nossa atmosfera, surge a aurora. Então, isso é a razão que a gente tem a aurora, e principalmente tem no Polo Norte e no Polo Sul, porque esse é o lugar onde o campo magnético entra na nossa atmosfera. Então, essa daqui é principalmente a maior a maior evidência que a gente pode experienciar do clima espacial é justamente a aurora. Mas, então, a gente sabe que muita energia entra na nossa área ao redor do nosso planeta. Então, quais são os impactos? Então, isso daqui é para mostrar as áreas e a tecnologia que é impactado pelo clima espacial. Então, começando aqui de cima, no Sol, podemos ver que o raio-x, aquela energia que vem em forma de luz, o que acontece é que esquenta a nossa atmosfera. Quando esquenta a nossa atmosfera, a atmosfera expande, obrigado, outra palavra que eu estava procurando, e quando expande, aí a densidade dos satélites que estão em órbita vai ter uma densidade maior, porque a atmosfera está expandida. Então, o que acontece é que vai ter um arrastamento, chamado, correto? O arrasto sobe. E depois, o que é que acontece? Não, quando sobe, então o arrasto é maior, então o satélite vai cair um pouquinho, porque o arrasto. Então, sim, com Starlink, sim. Em fevereiro do ano passado, daqui um ano passado, Starlink soltou uns 50 e tanto satélites lá para comunicação, botaram numa altitude baixa para ver se estava todo mundo funcionando. Naquele momento, chegou uma tempestade solar, o arrasto cresceu, foi para cima e eles perderam 39 satélites, porque não estavam prevendo que isso ia acontecer. E aquilo não era uma tempestade grande, era bem pequenininha assim, mas isso aconteceu. Então, o que está dizendo aqui é que porque nós estamos cada vez botando mais coisas no espaço, dependendo mais da tecnologia do espaço, estudando o clima espacial, ainda é mais importante hoje do que era 10 anos atrás, certo? Ou 20 anos atrás, porque a gente não estava usando o espaço tanto como estamos usando agora. Então, tem esse negócio da atmosfera expandido, também tem radiação, se a gente tiver astronautas lá na Lua, ou indo para a Lua, ou indo para Marte, uma tempestade vem, a gente tem que proteger eles, então a gente tem que prever isso. E também outra coisa, quando tem essa tempestade magnética que causa a aurora para ficar bem expandido e também mais intenso, também causa currents. Como é que se diz current? Corrente, pronto. Uma corrente nos fios elétricos, e se tiver muita corrente, entra no transformador e queima o transformador. Se o transformador queimar, e já tivemos ocasiões disso em 1989, parece, que em Quebec, sim, no Canadá, houve um negócio assim e tirou o power, como é que se diz? A energia por 8 horas. Isso foi também uma tempestade não muito grande. Então, agora a gente já tem o campo magnético, o campo elétrico, os fios elétricos temos mais, então o impacto vai ser melhor. Se uma tempestade muito grande, como ocorreu em 1859, se tivermos uma explosão daquela e atinge nosso planeta, pode tirar uma área tamanho do sul do Brasil, sem energia. É o Carrington Event. Essa é o Carrington Event de 1859. Se isso acontecer hoje, nós não estamos preparados. Então, Clésio faz muito melhor para espantar todo mundo, mas não é para espantar ninguém, mas é para saber que a gente tem de entender essa coisa e temos que observar. Então, isso é... Sim. Desculpe. Certo. É que eu estava falando com ele sobre depois. Então, o que é que a gente está fazendo sobre isso? Uma coisa que a gente está fazendo estamos lançando uns CubeSats. Então, tem esse CubeSat, o Sport. O Sport tem o melhor nome de CubeSat do mundo, que eu vou dizer logo agora. Você pode ver que meu sotaque talvez seja um pouquinho do Nordeste. Você sabe que tem um clube de futebol chamado o quê? O Sport. Muito bem, muito bem. Então, esse satélite tem um nome porque eu botei o nome de esporte, certo? Por causa disso. Mas, então, isso é verdade, mas isso não é a primeira, não é o que eu estou querendo falar. Eu estou querendo dizer que o esporte vai estudar as coisas que vão nos ajudar a entender sobre os impactos do clima espacial, principalmente o impacto na ionosfera e na comunicação. Então, o esporte foi lançado em novembro, no finzinho de novembro. O professor Loures foi lá que assistiu o lançamento e a gente tem o prazer de dizer que no finzinho do ano passado, o esporte... Eita, não tá... Daqui a pouco vai sair. Deixa eu ver. Pronto. Você pode ver que tem 2 satélites que foram lançados do ISS na mesma hora. O de baixo é o Sport e o de cima é o outro CubeSat chamado PCTec. Então, esse satélite a gente está trabalhando com o satélite agora. Também os satélites não são chamados somente do esporte, mas o satélite foi construído aqui no Brasil. Então, essa é uma coisa que a gente pode fazer. Os instrumentos foram fornecidos pelos Estados Unidos. O professor Charles vai falar mais sobre isso, que ele era o investigador principal do esporte. E Cássio não tem nada a ver com o esporte. Não sei o que é que está acontecendo aqui. Opa! Pronto. Certo? O clima espacial está perturbando agora. A gente não sabe o que está acontecendo no Sol, mas eu acho que... Chegou. Certo. Não sei porque... Certo. Bem, enquanto eles estão corrigindo isso, eu vou somente terminar só para dizer que tem lugar para todo mundo participar nessa, como eu disse hoje, essa aventura de estudar não somente sobre o clima espacial, mas como é que a gente pode botar outras pessoas na Lua e em Marte. E é um estudo avançado, é difícil, mas tudo que é bom é difícil, né? Nada que é para ter um progresso bom, geralmente é muito difícil. Sim. Pode fazer o que quiser aí. Talvez eu vou terminar aqui e botar de novo. Certo, então, eu vou continuar falando aqui. Última coisa que eu vou dizer é que a heliofísica, pelo menos lá na NASA, estudamos o clima espacial, mas também vamos ter, a gente está chamando a coisa que a gente vai fazer no próximo ano, bem, iniciado no fim desse ano, é chamado o Ano Grande de Heliofísica. E é tão grande que é mais de 12 meses. Mas é um ano grande de heliofísica, vai começar com um eclipse solar, que vai acontecer em outubro. Esse eclipse solar vai começar, e daqui a pouco a gente pode ver o mapa, mas vai começar na América do Norte, vai passar entrar em Califórnia, passar pelo Texas, depois vai para baixo, para o México, e depois vem para a América do Sul e passar assim na área norte e nordeste do país aqui. Então, isso é um eclipse solar anular. Anular quer dizer que a Lua está um pouquinho afastada da Terra, então não cobre o Sol quando a Lua aparece entre a Terra e o Sol. Então tem esse anel de luz que ainda passa através da Lua. Então é um eclipse solar anular. Então isso vai acontecer. Então não sei se alguém... Eu acho que lá em Alcântara vai passar bem em cima da Alcântara e lá para Fortaleza, naquele rumo daquela trajetória. Então, vamos começar... Sim. Desculpa. Então, isso vai acontecer em outubro. Depois, em abril do próximo ano, 24, vai ter uma eclipse solar total. Agora, essa, infelizmente, não vem para a América do Sul. Só vai passar lá na América do Norte, passando por México, entrando pelo Texas de novo e subindo para o norte. E naquela ocasião, é um eclipse total do Sol. E é uma coisa espetacular. Alguém já viu uma eclipse solar? Você já viu? Você viu também? É uma coisa que é que nem a aurora. Quem já viu a aurora também? Bem, você já viu a aurora? Muito bem. Não é uma coisa que não pode descrever, né? É uma coisa que assim você vê e pode tirar foto e coisa assim, mas tem de experienciar, tem de ter uma experiência com a aurora, também com um eclipse. Então, mesmo um eclipse anular, se tiver condição para ir para ver, seria uma coisa muito boa. Então, no finzinho do ano grande, vai ser em dezembro de 24, quando uma das nossos satélites, chamado Parker Solar Probe, essa é o satélite que vai bem pertinho do Sol. Talvez vocês já ouviram, já passou uns 12 vezes perto do Sol. Vai passar ainda a 13ª, mas na 14ª vai chegar bem pertinho do Sol, a aproximação mais perto do Sol que a gente já teve. Quando eu estou dizendo bem pertinho, dentro da atmosfera do Sol, vai passar assim uns 13 solar radii. Como é que se diz? Como é? O raio... radius. Radius, pronto. Raio, entre 13 raios do Sol, isso é muito, muito perto. Para estudar o que é que está acontecendo com o Sol, e a gente depois, com outras observações, podemos entender mais como o Sol funciona. Então, com isso, eu vou... Sim. Certo. Tá bom? Certo. Pronto. O Artemis é um programa internacional cujo o Brasil é um signatory do Artemis Accords. E o Artemis é esse projeto de botar pessoas na Lua, depois para Marte, né? Então, tem várias Vão ser vários lançamentos no foguete maior que já foram feitos, o SLS. Primeiro, já tivemos o Artemis 1, que passou no ano passado, no finzinho do ano passado. Passou 3 semanas fazendo umas órbitas que vão aparecer, que vão ter quando a gente vai mandar astronautas. Então, essa não tinha pessoas dentro do Artemis. Agora, o Artemis 2, vamos ter pessoas dentro do Artemis e também vão ter a órbita, um treino para depois, em Artemis 4, é a primeira vez que vão baixar pessoas na Lua. Não somente tem esse lançamento do Artemis com a cápsula com os astronautas, mas também tem esse Gateway. O Gateway lunar é uma estação espacial que vai fazer uma órbita através da Lua e vai ser como um lugar para estágio de astronautas. Eles vão lançar daqui da Terra, vão para o Gateway de lá, vão descer para a Lua, da Lua vão subir para o Gateway e depois voltar para a Terra. Então, essa é o início do programa de Artemis. Isso tudo para aprender como é que a gente pode ter uma presença sustentável em outro planeta, quer dizer, na Lua. Bem, a Lua não é um planeta, mas você sabe o que eu estou dizendo. Fora da Terra, uma presença sustentável fora da Terra. E a Lua é o primeiro passo, o segundo passo já é Marte. Então, estamos preparando com os objetivos, não só da Lua, mas também da Marte, e a arquitetura. O que é que a gente está precisando para ir para a Lua, que agora está bem desenvolvido, agora a gente está falando o que é a arquitetura que a gente precisa para ir para Marte. Em todo esse negócio vai ter o pessoal, os astronautas, não protegido pelo campo magnético da Terra. Então, prevendo esse clima espacial muito importante para a proteção e para o health, para a saúde dos astronautas, né? Então, a gente está trabalhando para entender o space environment, o clima espacial, para poder prever. A gente, geralmente, quando indo para a Lua, coisa assim, a gente está prevendo, mas a computação é tudo feito aqui na Terra, né? A gente pega os dados, faz a computação e manda o recado, vocês têm de esconder lá no lugar para se proteger, né? Mas quando ir para Marte, a gente não pode fazer isso. Então, a gente tem de ter essa capacidade dentro da aeronave, fazendo os medidos, sem contar com o pessoal aqui da Terra para essas computações, esses modelos, essas simulações. A gente tem que ter isso tudo dentro da aeronave onde estão os astronautas, ou pelo menos um lugar lá perto de Marte. Então, a gente também já está prevendo qual é a arquitetura que a gente tem de ter. Como é que a gente tem de observar o Sol? Como é que a gente tem de observar essas ejeção coronal, que chega para Marte também. Agora, Marte não tem muito bem. Agora, Marte não tem... é daqui... bota um pouquinho mais. Marte não tem mais um. Pronto, parei. Marte não tem o campo magnético, então essas ejeções coronais não vão ser um problema, mas a radiação vai ser muito importante. Então, pronto. Isso é o Artemis, a gente já está aprendendo, a gente está contando, isso não é uma coisa só dos Estados Unidos ou da NASA, é uma coisa que é uma internacional, a gente está trabalhando com muitos outros países, lá da Europa, o Japão, os canadenses, agora com o Brasil e outros países. É uma coisa internacional, não é 21. E daqui a pouco talvez tenha um pouco mais, né? Que a gente ainda tem. Eu acho que a América Latina deve participar maior do que o Brasil entrou agora está puxando os outros, né? Então, sim. Sim. Rollman, sim, no Apple. Sim. Tem uma série, sim, uma tempestade. Então, For All Mankind é uma novela em Apple TV para assistir lá. Mas isso, a gente tem que ter conta com isso. Tem outras coisas de... Não, vou falar isso não. Certo? Então, pronto. Tem esse daqui são a primeira solar eclipse anular, vai passar por aqui. Depois... Você está vendo que passa pelo Brasil nessa área, certo? Bem, não passa pela Alcântara, mas bem pertinho de Recife, olha. Certo? Eu acho que eu vou lá para assistir. Então, tem essa coisa. Tem diferença? Não? Os dois ao mesmo tempo, pronto. Agora eu confundi um negócio. Esse daqui é um vídeo. Sorry, I'm taking a little time here, Charles. I hope it's okay. Okay. Lá no finzinho. É um vídeo mostrando o Parker Solar Probe, que está passando bem pertinho do Sol. Mais um. Esse. É um vídeo? Não? Bem. Pronto. Ainda está carregando. Bem, esse daqui é o Parker Solar Probe aqui em cima. E se o vídeo passa bem pertinho do Sol e observando o Sol de uma maneira espetacular. Certo? Então, não tem problema, não. Certo. Então, eu vou deixar o vídeo aqui depois com ele para saber que funciona. Então, para terminar, eu fui um pouco longo, mas isso é sobre o clima espacial, isso é principalmente o que a NASA está fazendo. É importante, esse satélite pequeno tem uma grande parceria com as outras missões e, principalmente, isso é um jogo que vocês podem entrar para jogar também. Certo? Obrigado. Então, agora eu tenho o prazer de introduzir Charles SWENSON. E ele vai... Agora, eu falei de muita coisa aqui. Esse é o cara que sabe de tudo sobre o satélite pequeno, certo? I'm just telling you, you know everything about the small satellites. He's going to speak in English, and so you'll understand because he's a great teacher. He's a teacher, and if you ever have a chance to work with Charles and his group, please, time does not wait. You should take advantage of it. Okay.
Well, thank you. I'm honored to be here. And I wonder if my presentation will play. You wanted my computer? Ah, okay. There's what? Oh, they're going. Yes, let's try that one and see what happens. If the movies don't play, I'll be sad. Okay, let us begin. If I can figure out how to do this. Okay. So today I'm going to mess up. Okay, so I'm going to introduce myself a little bit. I'm going to talk a little bit about small satellites, and I'm going to use the Small Satellite Conference to talk about small satellites, and a little bit about sport, and I'm not going to talk much about this. So I'm Charles Swenson, a professor at Utah State University in electrical and computer engineering. And I have been at a number of different locations on sabbatical over my career at the Aerospace Corporation, which many of you have probably heard of Los Alamos National Labs. The Aerospace Corporation is effectively a national labs for space for the U.S. Department of Defense. And I've been at NASA headquarters a little bit as a discipline scientist. And anyway, I'd like to tell you a little bit about research motivation. Years ago, when I was a young professor and just starting out, one of the NASA scientists took me aside at headquarters and said, you know, we really need people not to solve easy problems in space. We need people that will work on hard problems and maybe not make a whole lot of progress, but it's the hard problems that we really need people to work on, not the easy problems. And so the hard problem that I chose when I was younger was, how in the world can I make lots of measurements in the space environment in different locations so that I can really understand space weather? And that's a hard problem because we didn't know how to do that. We didn't have any idea. And the idea generally was, well, let's make satellites smaller so we can afford to put up more so we can solve this problem. But that means that we have to convince people that we can make satellites smaller and cheaper. Okay, so the other thing that I'm really interested in is plasma and optical instrumentations for making measurements of the space weather. You can call me a weatherman, but what I really am is a weatherman that builds the instruments for measuring the weather in space. And I'm excited about small satellites, CubeSats, and constellations. So, with that, small satellites. We generally break small satellites into a number of different classes that are mostly metric, or at least powers of 10 for the most part, where we start out with mini satellites, microsatellites, nanosatellites, picosatellites. And generally, CubeSats are kind of falling into this realm right in here. So, brief history of this conference that happens each year at Utah State University. It was started in 1986, about 37 years ago. And you can access it on the web, and you can access all of the presentations from all the different years on small satellites. They're all just available to you. The idea, what started this conference? And the problem was, back in the time, late 70s and early 80s, is that in the United States, space programs were getting bigger. Satellites were getting bigger, and they were getting slower and slower to get into space. It was just becoming a bigger and bigger problem. And the idea that generally the philosophy then was, let's build one satellite and put a lot of payloads on this satellite. And we called the satellite bus. And then we had the payloads, and together the payloads plus the bus made the satellite. And I like to make an analogy here. At least in the United States, we have school buses that are nice and yellow like this. And if the bus is the satellite bus, then the payload would be the children. And from a systems engineering standpoint, what you find is that when you put a lot of children on a bus, or a lot of payloads on a bus, they begin to be noisy and to fight with each other. They fight for seats and so forth, and for windows to look out of. And the same thing's true of satellites at that time. The idea was we'll build one bus and go up with all the payloads, but the problem is all the payloads wanted different windows or characteristics. And so the systems engineering to put the spacecraft together was very difficult, slowing programs down, making them much more expensive. And so, you know, the philosophy was we'll save time and money by putting lots of payloads on the same bus. And they found that that didn't actually happen. I've got a couple of pictures here. Here's Alpha Bus. This is a big satellite. This is what we mean by big satellites. And I like this picture here because this is a big satellite that fell over, and it was an unfortunate incident. And if you're not sure about that story, yeah, it was a big mess up. The technicians took the bolts out of the ring, and the idea is that they took the bolts out, but the way that you work with these satellites is that normally they stand up, and then the mechanism lifts them up so that they're horizontal so that people can get and work on the satellite. And they took the bolts out and put them in another satellite that they were working on. And then when the next team came back to work on this one, they didn't follow the procedure. They didn't warn the people. They didn't follow the procedure. They didn't check to see that the bolts were in place, and they lifted it up and it fell over. So that's the demise of big satellites. So the motivation for small satellites, I've kind of said, you know, there are multiple payloads and multiple purposes. Costs were increasing. The ability to build such satellites was concentrated in very few organizations in the United States. The time between launches was increasing. Young people felt shut out of a career in space. People would go in to NASA or these organizations and expect to fly a mission, and they didn't, you know, after 10 or 12 years of working. So in '86, a small contingency of people got together to promote smaller, less complex satellites. About 50 people attended, and it was chaired by Dr. Frank Redd, one of my professors when I was doing my master's program back in the day. Over the years, and there's been a lot of them, we have chosen different themes for the Small Satellite Conference. Things like how do we use big data, data analytics with small satellites? How about satellites going to the moon and space? What are different architectures? Are small satellites driving a revolution? And this year, the theme will be missions at scale, which is scaling up small satellites to attack bigger and bigger missions. Almost a constellation kind of a theme. Okay, so here's a chart that I like to show that kind of shows the growth of the small satellite industry by looking at the attendance of people coming to this small satellite conference. And you see that, you know, just before the pandemic here, we were at about 3,500 or so attendees, which is kind of what we were this last year also. During the pandemic, we broadcast the small satellite across, just freely streamed it, and the number of attendees went up to 5,000 attendees according to the streaming. And this year, in August, it will be streamed too. So if you are interested and can't go to the United States to attend the Small Satellite Conference, you can view it and stream the proceedings locally and get at it without charge. Okay, so here's one slide that I also want to show about how small satellites are affecting the way we build satellites. Years and years ago, I would talk with people and I would say, you know, by the time we learn how to build really good small satellites, it'll change the way you build big satellites. And what I've got here are 3 different classes of satellites. These were the super microsatellites. These were the microsatellites, and the green are the small satellites. And of course, we have time coming along here on the bottom axis. And then on this axis, what we're plotting is the pointing accuracy of the satellites. What the pointing accuracy that the various missions used. And you see that basically over these decades from the 1990s out to the mid-2000s, late 2000s, you see a steady kind of increase in the precision of the pointing of satellites based on all of these different kinds of missions, more or less. And you see an improvement over time that we like to see. And then what happens is the nano satellites start to come in, the CubeSats. And it opens up the small satellite or the satellite industry to lots more people. More people get involved. And when more people get involved and more brain power gets involved, things change. And we start out with pico satellites that can only point to maybe, 5 degrees, 10 degrees, or so accuracy. They're using magnetic pointing systems and simple sun sensors and so forth. But rapidly, the very smallest satellites make it down here and shows an increase in our ability to improve our technology. And I mainly attribute this to including more people in the process. Okay, so yes, the small satellite revolution is changing the way big satellites get built these days. Okay, so now I'm going to talk a little bit about sport. So, for sport, I'm going to talk a little bit about the history, say maybe a little bit about the status along the way, and I'm going to spend some time talking about the science of sport because everyone needs to know the science of sport. Most important topic of all. And then talk a little bit about the instruments and the spacecraft and where we were. So, sport really started back in November 2014 with a Brazilian Air Force officer, Pierre Matei, who said we should do something with the United States in the area of small satellites. And they got together and met, and these are some pictures from some meetings in Brazil and some meetings up in Marshall Space Flight Center in the United States, and they decided that maybe what ought to happen is we ought to build a small satellite together. Then the result is that they went looking for people that could help devise a space weather mission that could go on a small satellite. And this is when I first got invited down here. I'm hiding out here. There's that Jim Spann guy that just spoke. I thought it was really nice of him that he couldn't remember some of those words in Portuguese. It made me feel better. Anyway, we met down here, and that's where sport got formulated. From there, it required a number of agreements between the countries, and sport turned out to be this process that enabled a lot more interaction between the U.S. and Brazil in space. Most recently, because it forced the two countries and the administrations of the countries to get together and sign agreements about what they would do together. Oh, did you do that? Is it true? There you are, yes. Thank you. We wouldn't have gotten it done without. We needed that kind of stuff before the technical stuff really worked on. But anyway, we had a number of successful design reviews in the United States and in Brazil as we put together the spacecraft. And the concept generally was that the United States would provide the science instruments and the launch, and then Brazil would provide the spacecraft and the operations, and then jointly we would work at the science data analysis. And it's a partnership with no exchange of funds. We both bring something to the table, put something together as a partner, working together as partners, equals, and then getting something of value out at the end. And there's a number of different organizations that we can point out, both from Brazil, and we would like to thank AEB and NASA, and then the science providers, the The Aerospace Corporation provided a science instrument, the University of Texas, Dallas, and Utah State University and Goddard Space Flight Center, which apparently isn't on that list. Okay, so now let's talk about forecasting the weather. So we envision, you know, at some point, this guy's name is actually Jim Spann. He's a famous weather forecaster in Huntsville. Is it Huntsville, Alabama? Birmingham, Alabama. Okay. This is Jim Spann's look-alike, and he really does, you know, forecast the weather on the news, okay? And we envision, and you know, Jim Spann envisions also, that in someday space weather will be forecast on the news. And someday you will tune in to see when the coronal mass ejections are coming off and when we expect to see radiation events at the moon. And, you know, is it going to be safe to travel from Earth to Mars? And we will be paying close attention to space weather, just like we pay close attention to terrestrial weather. Okay, so how do we forecast our terrestrial weather? And what we do is we take a whole bunch of measurements all over the ground, in the sea, and couple it together with some images from space. And then we go into very sophisticated computer systems. These provide initial conditions about what the state of the atmosphere is. Very sophisticated computer models then crank out our forecast. And if we're going to ever do space weather, then we need to do the same kind of a thing, and we need lots of measurements at different locations in order to know the initial conditions to be able to use our space weather models that we're still working on from a science standpoint, so we can predict space weather and know whether it's safe to travel to Mars or whether our satellites around Earth should go into some protective mode or something like that. So if we look at space weather stations, there are a number of space weather stations in Brazil, and there are a number of space weather stations around the Earth looking up at the Earth's ionosphere. But really, the density of measurements is not there, and thus we probably need space multi-point measurements in the space environment to really be able to make progress on this. So, basic space weather instruments. What do you want to measure when we're talking about space weather, and specifically space weather in the Earth's ionosphere? Well, in the troposphere, we like to measure things like rainfall and temperature of the atmosphere and air pressure and wind speed and direction and humidity and cloud cover. And these are the kinds of things that go into the very sophisticated computer models and that we crank out our predictions from. And in an analogous way, I've made a list of the kinds of things we would like to be able to measure in the space environment. I've tried to line them up in some kind of analogous way, but you know, rainfall, radiation doses, temperatures, densities, plasma drift speeds, plasma drift directions, composition of the upper atmosphere. And you know, we have clouds that make it so we can't see the sun, and we have scintillations that make it so that we can't see the radio signals from our satellites and other places. Okay, so one of the key things here that affects Brazil and that the SPORT mission is going after is this concept called plasma bubbles. And I don't know if this is going to play. I'm going to be sad if that doesn't play. Jim, are you going to, well. Yeah. This is my fear, that we put it on a drive and not here. But anyway, plasma bubbles, this is supposed to represent the ionosphere, and this is low density, and as we get into the red, it gets to higher density, and we see this is about 400 kilometers, and it begins to trail off as we go up. And what we see are these bubbles that actually kind of look like some kind of lava lamp. I don't know if you know the term lava lamp, or, you know, oil and water thing that we flip over. Yeah, none of these videos are going to play. I'm just about ready to put this over on my computer. Yeah, they're not going to play. This is all lovely. Okay, so the problem is these bubbles rip up and they have a effect on our radio communications passing through the region. And the analogy that I like to make is to say, look, here is water, and we all know that water is clear to light, and you can see through it. Okay, and here's air in bubbles. And we know that air is clear and you can see through it. So why is it that when you put bubbles into water, both being transparent to light, that you break up the light and you can't create images and you can't see very well through it? And you all know it has to do with the index of refraction between the two materials, and the light gets scattered. That's exactly what happens with these plasma bubbles. They rip up through, they create bubbles of low-density plasma, or air, if you will, in the ionosphere, lots of them, disturbances. And the ionosphere, normally, if it's not disturbed, is transparent to electromagnetic radiation that's high enough frequency. But the two of them together cause the radio signals to be disrupted and cause scintillation. Okay. So what do these scintillations, and this would have been lovely if we could have talked. Playing. But before we get into this, I want to talk about what is a scintillation. No, yeah, this thing's not. Okay, so here's your class in radio signal modulation. We all know that we transmit information on radio signals that look like sine waves. So here's your mathematical formula for a sine wave. You have an amplitude, you have a frequency, and you have this number, that's the phase, that is kind of the shifting it back and forth along on the time axis here. And if we amplitude modulate a signal, we might have one amplitude and then another amplitude, higher and lower, as we're transmitting ones and zeros and ones and zeros. And if we do frequency modulation and change this value in the same way, we might send out a frequency of a sine wave and then a lower frequency and a higher lower to represent our ones and zeros. And if we do phase modulation, then what we do is we change this value, and so we have the same frequency of wave, but every once in a while we shift it. It's like shifting it back and forth on the axis, and so we see these kind of discontinuities, but the sine wave has been shifted in time, and those time shifts represent three different ways. So what happens when these signals encounter these radio plasma bubbles? And I'm going to show you what this looks like using some data from a mission called Cosmic 2. Here's the Cosmic 2 satellite. This is a joint US-Taiwan mission. And on the Cosmic 2 satellite is a radio transmitter that's broadcasting pure sine waves, just pure sine wave radio frequencies at UHF, L, and S-band. And as these pass through, and this is a simulation of a plasma bubble, 200 kilometers down here, working its way up to 800 kilometers. And you see this bubble working its way up through the plasma. And we receive the signal here, and how does this affect the measurement? And the first thing that we have here is our measurements at this location of the satellite as it passes over at UHF, L-band, and S-band, three of them. The first feature that you see, time is going this way, so we first see the frequency of the satellite's transmission at higher frequency, and then as it passes overhead, and then it moves down to lower frequency. And you're all familiar with that Doppler shift as the ambulances zip by and you hear the higher and the lower frequency. We're seeing the Doppler shift at UHF, we see it at L-band, and we see it at S-band as it passes over. And what we calculate are some parameters that tell us features. How has the amplitude of this pure sine wave been affected by the scintillation? How has the phase been affected by the scintillation, the bubbles passing through it? Okay, here's some example of data collected by this system. And at the top, we have the power that's coming in at UHF and at L band and at S band. And in general, these look, pretty flat and nice. These red lines are predicted values that nominally where the system should fall between. Down here, we're breaking the signal up into a spectra, and we're just showing right around the carrier frequency, plus and minus 200 hertz for each of the different frequencies, and the intensity. And then what we are doing is we're calculating some values here. The blue is how the amplitude's affected, and the red is how the phase is affected. Okay, this is a quiet pass. There's no ionospheric disturbances. And then we have a bubble, and we pass through, as the satellite passes over, the signal passes through the bubble. And what we see is dropouts here. The blue is showing you kind of the changes. You can see the changes in amplitude. And when we look at the frequency plot, we can see that the frequency is being spread a little bit by, hundreds of kilohertz or so, less here at S-band. And then when we look at our different metrics to measure how the amplitude's changing and how the phase is changing, well, we see very similar patterns, and they correspond with when we're passing through bubbled regions in that line of sight signal. Here, here, here. Very strong at low frequency. And then when we get to L band, look at this. We see that the amplitude variations are reducing, but we're still seeing strong phase or shifting back and forth of the signal due to the plasma bubbles. And then, as we look at the same thing, making the measurement at the same time at S-band, the amplitude fluctuations are just about gone, but the phase fluctuations remain. And you can see that they are very similar at all three different frequencies. These are the kinds of things that engineers have to worry about when they're building a communication system. They may not see a power change, but they can see a phase change in the signal that's introduced by the plasma bubble being present. And that affects our modern communication systems that are using phase shift keying types of signaling constellations. I'm going to just skip over this. Here is an example of a spacecraft. It's called Timed, and it had an ultraviolet imager on it. And it was going around in a more or less polar orbit. And it takes about 15 orbits for this satellite, the satellite makes 15 orbits in 24 hours or in one day. And the orbit had been designed so that the Earth rotates underneath so that the 15 passes can be seen. 1, 2, 3, each of these is a pass as this satellite looks down. And so the Earth rotates underneath it, and it takes these swaths. And we can see in the ultraviolet the recombining of the electrons in the ionosphere with the ions in the ionosphere. And the brighter here, the closer to white, the more intense that signal is, which says the plasma is denser. So in general, we have this feature, and this is the magnetic field lines of the Earth. The green line is where the magnetic field line of the Earth is horizontal to the surface of the Earth. And we see in this region right here around Brazil that we have a little bit of a magnetic anomaly. And we can see in these images these dark lines and these dark features like this that are indications of plasma bubbles that have come up and decreased the amount of electrons that are in the ionosphere, and so they're darker. We can see that this one is curved because the winds are blowing it. It came up quickly, probably as a line because they follow the magnetic field lines north and south and kind of create a fan structure, whole fan structure, kind of a two-dimensional type structure that sticks out here in altitude. And then after it stops, the wind bends it into an arc. But it becomes more complicated in the Brazilian, South American sector because of this magnetic alignment that takes place. So this is a very interesting region to study these plasma bubbles and why it affects communications, how frequently do they occur. And this is just one more thing on the plasma bubbles. This is a plot showing time. So this is noon, and this is midnight. And then we have altitude this direction. And it's showing this is a computer model showing the density of the ionosphere. And the ionosphere gets more dense as the sun rises and shines on the ionosphere, and the UV from the sun creates plasma. And then right after sunset, something happens and the ionosphere is uplifted, and then sometimes we have plasma bubbles that form in this 18 to 22 local time kind of hours. This is when plasma bubbles occur pretty regularly in the evening. Okay, so SPORT has a number of instruments on it for measuring plasma motion, plasma density, small-scale structures and waves, scintillation index, magnetic field structures, plasma temperatures, and there are a number of instruments that provide these measurements that are a part of SPORT. And then these are kind of giving you an idea of what these instruments look like, these, at least the electronics. So we have the drift meter, we have a GPS radio occultation, a space weather, Langmuir electric field impedance probe, and a magnetometer system. And then that, together with the ground network that exists in Brazil, will be used by SPORT to study these plasma bubbles. The basic concept, the way SPORT has been put together, is that it was put in a nice soft stowage container, similar to the way the vegetables go up for the astronauts to eat, put in a Ziploc, cushiony foam bag in a container, sent up to the space station, and then this was taken out on the end of a robotic arm. It was passed through the crew module. The crew passed it out, the robotic arm grabbed it, pointed it in the right direction, and then SPORT was ejected on December 29th of 2022, and we are currently in the SPORT checkout phase. And where we are is that SPORT is slowly being checked out. We've had some problems with ground stations and being able to regularly communicate with it. Those have largely been resolved, and the spacecraft is power positive and thermally fine, and we are talking to it quite regularly. And we're right in the stage here now in the next few days of trying to get the attitude determination system up and running and get SPORT pointed the right direction so we can use the high-speed antennas to be able to communicate with it. And then we'll start to move into commissioning the science instruments. So we hope that progresses well over the next few weeks. Okay. This is a block diagram showing in general how the data from the science instruments flows through the bus that was put together by ETA and then talks to ground stations run by INPE, and then the data that's collected is put onto a cloud, essentially box, a cloud server for the U.S. Instrument team providers to retrieve it. They do the processing that turns the raw data that they collect into scientific measurements of density and wind speeds and so forth, and then pass it back to INPE, the Embrace Center, where it's made available to the entire scientific community to download. This shows you some nice CAD models of SPORT, and I have a lovely movie here to present which won't play. And then I have another lovely, this is the best movie ever, of SPORT being ejected, similar to the one that Jim showed, but much longer, showing what happens as time goes on as the two satellites separate. So we'll leave that to your imagination. Thank you very much for your time.
We have time for questions. More questions for each speakers. Yeah, we have at least one from. You should not ask anything, so you belong to the team.
No, but it's important for because times they say that satellites for universities. Big satellite is a serious game. And what do you think about that? The small satellites is out of the game to science or work in space.
First, we give questions. Asking more stick. Maybe if there's some left over, you can pick at the table. I think I have NASA. You ask him. But the real issue that Laura points out is. Uh-oh, I'm supposed to use the microphone. Okay. Okay, so the question that Loris asked is small satellites, they're toys, they're only for universities, for educational purposes. They're not real satellites. First thing I'll tell you, when you put a satellite in space and you're talking to it using radios, you can't tell whether it's big or small. You can't. They're just as complicated to run as a big satellite, and sometimes even more complicated because you haven't designed it well to be easy to run or operate, okay? So that's the first thing. The second thing is, and I toyed with throwing some stuff in here, but I'm running another program for NASA Earth Science Technology Office. And the objective there is, can we build a very capable CubeSat that can replace some of the functionality of satellite system that U.S. flies called Landsat. And I'm not sure if you're familiar with Landsat, but it's been running since the 70s, and it takes pictures of the Earth in multispectral bands, and then the data is made available on the web to whoever wants to use it. So Landsat's been a great resource for understanding things like deforestation over time and how the environment's changing and so forth. But it's an expensive program, and they would like to do it smaller. So I'm in the process right now of using a CubeSat, a little bit large one, what we would call sport is what we would call a 6U, a CubeSat that's 2.5 times larger than sport, to make better measurements than the current Landsat makes, okay? And it's a spacecraft that, yes, 2 tons, and this thing will be like, 30 kilograms. And we're using an advanced science instrument built with my colleagues at University of Hawaii. And this is a technology demonstration program for how we could do that. Why? Because the people that do Landsat also want multi-point measurements in the space environment. They would like to have multiple Landsats up so that they can really understand what's going on. If you look at what's going on in the commercial world, and personally I've been doing this for a very long time, more than 30 years, playing in small satellites and trying to get people to believe in them. I always thought NASA was going to fly the first big constellation of small satellites, CubeSats, to make measurements of the space weather. And I was completely wrong. Instead, there's a company called Planet Labs, which is flying hundreds of satellites that are half the size of sport, half the size. And with this constellation of satellites, they map the surface of the Earth every day. Every 24 hours, they map the entire surface of the Earth. And they sell those pictures as a geomapping resource kind of a thing every day. And it's done with 3U CubeSats. I will say that an institution that grew out of Utah State University that's called the Space Dynamics Laboratory has billion-dollar contracts with the United States Department of Defense to deploy small satellites. Why? Boy, small satellites would be a lot harder to take out in space than one big one. So, is it small satellites or toys? I have a lovely presentation that I could share with you on some of the technology going into this mission and the difficulties of doing some of these things on small satellites. And building a small satellite that has 250-watt solar panels and how do you deal with the heat on that kind of a mission. But, you know, this is the future. Everyone will be looking at trying to figure out how to build satellites that are smaller, and the innovation in this particular area of the space industry has just been astounding in the last few years. You look at what happened with the attitude control. It's not just attitude control, it's many space technologies are being driven by these small satellites. And yes, they are educational tools, and you know, universities can build them, and they may not be as fancy as the ones that Planet Labs are building, but still, you know, having been part of this community and watched this development for most of the last 30 years, I can tell you that small satellites are not going to go away, and they are taking over some of the jobs on purpose of big satellites. There you go, Loris. Did I do good? Okay. This is one of Loris's favorite topics. Oh, they just want stickers. Here you go. Thank you. It's our pleasure. Yes. Yes. So I think one of the biggest societal impacts that you experience here in Brazil of equatorial plasma bubbles and the resulting stirring up of the ionosphere and the scintillation on radio signals coming through it are from what we call navigation systems, GPS, okay? And what it means is it makes it really difficult to use GPS for automating things like aircraft landing. So, you know, you'd like to be able to not put in very expensive radio location facilities at airports, all airports across Brazil, so that in bad weather airplanes can still land. You'd like to be able to make use of GPS, but if you've got these problems of scintillation, then you can't use it. It's not precise enough because of that. The other thing is that if you want to do precision agriculture and you want your tractor to drive itself using GPS in the field and do the fertilizing or the weeding, you don't want it wandering because GPS errors. You know, that's a problem. So there's a lot of things that you can do with our global positioning kinds of systems, but it is problematic here in Brazil. So what do you do to solve it? Well, you know, the first thing that people say is use more satellites. Maybe if you track, you know, instead of the minimum 4 satellites, but instead tracked 12 or 16, you could get look directions that aren't passing through bubbles and you could make it work. But it's risky. You know, the US isn't going to put up all those, and so you end up using the US and the Chinese and the European, you know, location systems, and eventually probably even the Brazilian, because I think that's one of your strategic goals, is to put up your own navigation kinds of problems, but you deal with, you know, scintillation. The other thing is, you know, maybe you're going to do this with small satellites. What if you put your satellites below most of the bubble? You know, can you use lower altitude satellites to do your geo-navigation instead of really high ones that all pass through the bubbles? These are research ideas, things to think about. Other questions? Go ahead. Nebraska Huskers, good job. I know where Nebraska is. Yeah, so this is kind of the science of sport. What the current science community would like to be able to predict bubbles. They'd like to be able to know what happens right around sunset and be able to say, oh, I can tell what's going on at sunset, therefore you're definitely going to have bubbles at 8:30, 9 o'clock at night, going up until whatever. And we're not quite there yet. The U.S. has tried to do this a number of times. Sport is another mission. We have a specific, thing that we're trying to do with sport, and that is that if you look at different longitude sectors around the Earth, on some days sectors will have bubbles and other sectors won't. Why? And we know that it's tied in quite a bit actually to the thin winds in the high upper atmosphere, about the altitude where, well, pretty high. We'll just put it that way. The edge of space, kind of neutral winds, they have something to do with it. And also, obviously, the magnetic field orientation. And so we're trying to understand, just in general, what's the difference between the Brazilian sector and the other sectors around the Earth with sport. We have a fair amount of information in the Brazilian sector, but we don't have so much over Africa and the other sectors. And so flying sport gets us that information. We want to see whether, is it geomagnetic storms that is really one of the key triggers that kicks off bubbles. These are research questions that the science community is dealing with, and kind of what we're trying to do with sport. So I don't have an answer for you because that's what we want to know. And, we're struggling to find ways to answer these questions. Uh-oh. International space models, goals. Goals are models. Say that one more time. I'm old. Oh, regulations. Okay. Laws. Well, yes. With space, everything is done by international treaty, and the UN becomes one of the key organizing bodies. One of the ways that space is somewhat controlled across the globe is through the allocation of radio frequencies. You have to, since your satellite is high and is going to be emitting radio waves, it's probably going to emit radio waves across multiple countries. And therefore, that is negotiated at the UN level through an organization called the ITU, and also within the agencies of the various countries. But the licensing of that is what is kind of used in a regulatory sense to determine whether you're compliant. It's not the number of spacecraft that you can put up, but what the current law or what the current issues are is, what are you doing to make sure that you're not polluting the space environment so that we have collisions between spacecraft, etc. And the way those regulations are kind of being passed throughout the world is through, we won't give you a radio license to talk with your satellite unless you guarantee your satellite will come down within 25 years. And in the United States, these laws are actually in flux right now and becoming more restrictive, and suggesting that if satellites above 500 kilometers all need to have propulsion and need to be able to come down by propulsion. If you're below 500 kilometers or 450, then maybe not. These are discussions that are going on right now. It's quite an interesting field and question that you've asked, yes.
One more question.
Uh-oh. You're going to give him a sticker? It had international stuff. Okay, was there, who did you choose?
Yeah, he's my student, so it's
Okay.
his tour now.
I'm so sorry, you can grab me after.
When we talk about small satellites,
In space, orbital debris, yes.
yeah. There's
Okay, so I'm gonna go out on a limb and tell you my philosophy here that I've been trying to push into the space industry a bit. And that is what we worry about is some kind of chain reaction where one satellite runs into another satellite and splatters lots of small pieces everywhere. And then those pieces ram into other satellites and break them up into small pieces. And suddenly the Earth has a ring like Saturn, right? Okay. So that's the fear. And so the problem is there's been quite a bit of push and pull between the small satellite community and the large satellite community. And many in the large satellite community have said, obviously, small satellites are toys, and therefore they shouldn't be put in space because of space debris. We don't go into space unless we have something important to do in space. Basic idea. Don't put up anything unless it's going to do something important. And if you are going to put it up and it's maybe not going to do something important, keep it low so it re-enters and burns up in the Earth's atmosphere. But I've also been pushing back on that a little bit and say, well, here's the issue. Don't put up something big, because the more mass you put up, the more fragments it can make, and the more likely you're going to create this chain reaction. So don't put up anything with any more mass than you absolutely need. Keep it small in order to keep the pollution, the total mass that we put up in space, low. Now the question is, have we done a study? Have we done numerical studies to show, oh, if we put up a few big satellites versus a bunch of small satellites, what's the likelihood that we're going to run into problems? Well, maybe someday we'll get a PhD student at Utah State and do that kind of work. But for right now, we've just been talking about it kind of at that level. Yeah, 2.5 years if you're lucky, depending upon the solar cycle. Uh-oh, what's wrong? Oh my goodness. The sticker. Run to your test. Okay. Yes. Uh-oh. Help you. I don't know how to use an Android phone. I only use iPhones.
Presente em Marte, na Terra. A comunicação, essa resposta entre Marte, Terra, usando a mecânica da simultaneidade. A pergunta é, como é que a NASA vai apresentar teletransporte?
This is a tough one.
Oh, okay.
Well, he's saying that there is some already. Yeah.
Well, give it to the lawyer.
No, he asking about some experiments about some subparticles that you use one particle in one place on the universe, and the particle reacts in the other place of the universe. So you can have an instantaneous reaction in this particle. So we can do instantaneous communication, or for beaming, the beaming up, Scotty, reality in the future.
Jim?
Jim?
No, I think you're getting at quantum cryptography and, this idea in quantum mechanics that, as Einstein put it, spooky forces acting at a distance, that cause two different particles to be entangled with each other. And where is that going to take us, and how is that going to affect space and communications? That's a really deep subject. There's a lot of work obviously going on in this area. There have been a number of satellites flown that have demonstrated quantum entanglement, but mainly what people are doing is not instantaneous communication, but to be able to ensure that the signal transmitted from point A to point B hasn't been even intercepted, because if it was, then the entanglement would be broken. Uh-oh.
Thank you. Thank you.
Go ahead.
Plasma bubbles.
Yes.
Okay. Those goes up.
Yes.
Could plasma bubbles break? That's
Yeah, yeah. Like an updraft for an airplane or something like that. No. You know, we say that space is a vacuum for a reason, and anything that has any sizable mass is really not affected by it. What's really affected are the photons passing through the bubbles, not so much that there is enough momentum in the bubble lift to affect any object of significance. It's a pretty good vacuum up there. I will take questions until someone tells me I have to sit down. And you're in charge now? Okay. Okay.
I don't know what kind of or something.
I don't have anything to do this evening. Jim's in charge of me and Loris is in charge of me because I can't speak Portuguese, so whatever they say, I do.
Okay, let's have a couple more questions.
Okay. Tomography. Tomography is kind of the thing, so like a tomographic X-ray, and reconstructing the bubble. And now there have been a number of studies and attempts to do that, but it requires a number of receivers laid out on the ground, because as you're going to do tomography, you look through the region in different directions in order to be able to do the tomographic reconstruction. Colleagues of mine have tried to fly receivers in space and use transmitters on the ground to do this reconstruction. It's really right at the edge. I wouldn't say that anyone has really successfully done that at very high resolution. In theory, and absolutely in theory, it's possible. I've got another colleague at Embry-Riddle, one of my old PhD students, that I think might actually make it work here in the next few years, where he's using the GPS signals as the signal passing through and trying to be able to do the tomography. And the basic idea is, well, I can get a whole bunch of GPS receivers and lay them out on the ground and not cost too much money. And so I'm waiting for his experiment that'll happen in a couple of years on this. Yes?
Sorry, second question.
You only get one sticker. Even if it's two questions, it's only one sticker. I'm sorry.
All right. Would it have utility? Would it be useful in some way for studying the bubble?
Well, you know, one of the things, you know, they're pretty ephemeral, you know, hard things to study and see. And we sit down and work on our mathematical calculations on these Rayleigh-Taylor instabilities, generalized Rayleigh-Taylor instabilities, you know, that show them coming up, and how do they bifurcate, and how, you know, how big do they become, and how do they grow, and you know, they're numerical models, and they look really pretty, and I've showed you some, you know, and you say, boy. But people sit back and say, I would really like to know if that's real. And so that's why people want to do the tomography. They really want to capture the bubble in high enough detail or resolution to compare to the numerical models to see if we really understand all the physics as they propagate up and bifurcate and so forth. You know, it's just part of understanding nature. And if we could have that ability to really see the bubble, I mean, we look at the bubbles, you know, and Brazil does this all the time with all-sky imagers that are looking up and watching the recombination of the electrons and the ions, and they take pictures. But, you know, there are these big, dark, amorphous things in the sky, and you know, it's a two-dimensional thing, and you're looking at it down through it, you know, kind of a projection down, and, you know, the theorists aren't really excited. But if you could do tomography, they'd be really excited. Anyway. Uh-oh. Who's in charge? You're in charge. Well, first hand him a sticker. So the question is, hey, what can I do at this university to get involved? I'd really like to go work at JPL or NASA, where all the activity is happening. And do you want to take this? Here you go, Jim. You can answer in Portuguese too.
So the question was, how can I go work at NASA? Is that the question? Or
how can he get involved in space at this institution?
Oh, at
how
this?
can Brazil contribute to space and all these activities?
Ah, sim, sim. Ok, tá bom. Ok, there are tem várias opções que você pode seguir. Uma é realmente procurar um intercâmbio entre uma universidade como essa e uma universidade lá nos Estados Unidos. Por exemplo, a ITA e o Utah State já estão tendo esse intercâmbio com estudantes. Então, isso é uma possibilidade. Também tem outra possibilidade que, pelo menos com a NASA, tem um internship, não sei como é que se diz em português, mas é uma oportunidade de um estágio de estudantes e estrangeiros, quer dizer, não são americanos, mas também podem participar nessa área. Então, você tem de fazer um Google no NASA Internships, aí, 2 palavras. Então, lá tem as instruções e mais informações. Mas eu acho que a maneira mais direta é procurar, por exemplo, seu professor que estiver trabalhando com outros professores lá nos Estados Unidos, por exemplo, assim fazer crescer essa relação e um envolvimento, e de lá, porque é mais fácil para um estudante lá nos Estados Unidos para trabalhar na NASA ou JPL, qualquer lugar assim, do que a pessoa que não está afiliado com uma instituição lá nos Estados Unidos. Mas, então, isso seria o meu... Tem summer schools, não sei dizer em português, mas também tem escolas assim, 2 ou 3 meses, semanas lá nos Estados Unidos, especificamente sobre o clima espacial, por exemplo. Então, atender essas escolas é uma maneira boa de network, fazer um network. E, às vezes, muitos estudantes que não são americanos vão fazer o pós-graduado, os estudos em universidades lá nos Estados Unidos. Então, isso é muito comum. Mas, para ter esse networking, para saber quem está procurando estudantes na área que tem o seu interesse, indo para esses summer schools, e também para em convenções grandes, assim como AGU ou EGU, são essas... é caro para ir para lá, mas essa é outra maneira de fazer o intercâmbio e o networking, certo?
Você falou da JPL, do JPL.
Sim.
Olhar as universidades que trabalham diretamente.
Uhum.
Working directly with California. Yeah, San Francisco.
Well, I mean, many universities work with JPL. The California Technical Institute is the primary university that runs JPL, but many universities run JPL. I think if you find any area of research in space, you can make a connection back to a NASA center or JPL. So I think making that network and making that connection, desculpe, eu estou falando inglês agora, mas making that connection back to an American university, I think is the easiest way to end up working on a NASA project. That would be my suggestion.
I'm going to just add 2 bits into this. I have found that people in Brazil can think as well as people in America. You know, there's not much of a difference. You think just as well as we do in America. And I know you have professors here at this university who are very interested in space and trying to make things happen. The only other thing I would add is there's a lot of information out there that's freely available. I mean, if you really want to know a bunch about small satellites, go read the proceedings of the Small Satellite Conference for 30 years like I have, and then you'll know what I know. It's out there. Anyway. Yes. Okay. Yeah. Question about the plasma bubbles. Okay, so I think I understand that you're saying how can we measure the effects of plasma bubbles regionally?
No, I think that damage.
Oh, the damage
It's
done.
not as precisely from plasma bubble, but the energy that comes from the space from the or mass ejection. All this energy enters in Earth's magnetic comes Earth how this energy that comes from the sun enters in the Earth's magnetic field can create
Yeah. So the plasma bubbles, just like Professor Charles mentioned, is not enough to provide something to lift up. There's not physically a strong wind there. But the resulting impacts are significant, particular, not necessarily for plasma bubbles, other than they affect communications. And if you have broken communications, bad things can happen. For example, we already have pretty good evidence that a space weather event caused death of some people who were in a military operation because they were not able to communicate right at the particular time to provide instruction for them to leave the area, and as a result, they were killed. So the impacts, the resulting impacts, often is what is damaging. The one area, so radiation in space is a very big impact, and that's primarily on electronics that can cause failures, and we've seen that satellites lose control. Or personal health issues where somebody gets radiation much more than. And then the other significant impact, I would say, is these currents that are induced on large transmission lines can, if the magnitude of the storm is big enough, will cause the transformers to overload and fail. And replacing those transformers is very, very difficult. And space weather is not a local thing. It is a very widespread, and so you would damage a very large area, a third of the size of Brazil, for example. And to get that, and everybody depends on electricity. You don't have water, you don't have gasoline for your car, you don't have cell phone to talk to. Everything depends on electricity, and so that would be a very, very significant damage.
O efeito
Sim.
é meio como sobrecorrente. Está botando mais energia no sistema. Esse sistema, que essa energia vem do Sol, entra no campo magnético da Terra e ela entra nas linhas de transmissão. Entra nas linhas de transmissão, elas queimam os transformadores. Queimam os transformadores, você fica sem energia. Isso aconteceu em Quebec, 89. 8 horas, Quebec. A província de Quebec ficou sem 1900.
Mas se tiver um negócio bem grande, não é só 8 horas, não. A gente está falando de 8 meses, coisa assim. Então, é uma coisa... se tiver um negócio grande assim, vai ser difícil de recuperar. Certo? Sim, ok.
That's for you. Did you say for me?
Yes, he did.
You take him the sticker then. So how hard is it to launch small satellites in the rocket propulsion kinds of things? Hybrid rockets, yes. Okay, so, you know, small satellites, a lot of them are being launched as secondary payloads. But in the United States, what we're finding is that there are enough small satellites that they will get together and purchase a rocket ride that's can launch a Falcon 5, and they will launch all of these satellites on the Falcon 5, and they are going regularly. Now, the question of what is the utility of using hybrid, solid, gaseous kinds of rocket engines? Are they better? Are they, I have colleagues that have been working in hybrid rocket engines. They've been printing plastic on a 3D printer and print the rocket engine and the fuel all in one, and then they run nitric oxide or O2 through it and make rocket engines, yes. And there's a lot of nice things about hybrid, and we see at the Small Satellite Conference discussions about hybrid engines, but I haven't really seen it come to the forefront and take over from things like, the type of technology that SpaceX is using, or ESA is using, or the Russians or the Chinese are using. Hybrid hasn't been there. Maybe for upper stages, and maybe for small propulsion systems, it might end up being a useful approach. But anyway. Yes, you can come down. You don't have to ask questions anymore.